I tried to do the 2's complement negation,
Okay.
NEG.
So you found the NEG, but what sort of C code did you use to find it?
My C code was just int A equals 2, int B equals negative A, and then
Okay, so you just did that? All right. So he found 2's complement negation. We talked about 1's complement yesterday, the not instruction, right? That'll flip all the bits on something, and that's kind of 1's complement. And so 2's complement, or just taking something and making it negative, is the neg instruction. So 2's complement. That's how you spell that? Is that how you spell it? Is it complement?
E.
Complement. AKA making stuff negative. All right.
And then you said we could find a multiply in Visual C++?
Yes.
I didn't know if it counted because I looked it up, but
Okay.
if you cast it to unsigned long and using unsigned int.
Oh, that's unfortunate. Brad, I called on him before you. Yes, Brad emailed me last night as well saying he also looked it up. And did you find the Stack Overflow?
Of course.
Exactly. So, all right, so there's a Stack Overflow article out there where someone is saying exactly, why won't Visual Studio make a mul instruction for me? And what the people said was, put it up here, what the people said was, basically, they use imul because, well, I think the gist of it was they use imul because in C, if you have an int times an int, by default, the result is considered to be an int, and therefore, even if you overflow it, it really just truncates it back down to that 32, and whatever's on top gets thrown away. Just that's a C thing. And so basically, it doesn't matter. And then the other thing is, when you have these things which potentially overflow, it doesn't matter whether it's signed or unsigned as far as the lower 32 bits are concerned. So the upper bits will differ, but the lower ones won't, and therefore imul versus mul are equivalent. And so what the article also said is if you go to long longs, so if you go to 64-bit values and you try to do a multiply, then it'll put the result into a 64-bit value, and therefore the negative or positive will start mattering at the top. And so then if you do that, you'll get a mul instruction. And I have the simple source sample code that I think was equivalent of the Stack Overflow stuff that Brad sent me. So I'll show you that in a second as well. But yes, you get extra credit too, kind of. Everyone who got it by looking up, I give you half-point extra credit because you looked it up. All right, so that is unsigned multiply. All right, anything else? Nope. All right.
That was pretty lame. I just did a decrement.
Okay. Got a deck. And what instruction sequence did you use in C to get that?
Just minus there in a loop.
All right.
The biggest problem was just trying to get I originally was using Xcode, and I forgot to compile it for 32 instead of 64. So
okay. Gotcha. So he was using Mac and he compiled it 64. Actually, Dave also generated some 64-bit assembly, which we'll see in a second as well. So decrement a register. I think it only works on a register. I may be incorrect. You may be able to specify an RM32, but I think it's only a register. So, you know, that's subtract 1. All right, Amy?
I did not actually write the program, but I looked up in the book and thought that we didn't do anything with strings yesterday, so there were probably instructions related to string. The book says that you can move entire words.
No, we're about to talk about that example next.
Oh,
yes.
Okay. Well,
yep. So that's an example. There's definitely some repeated string operations. There's a single string operation instructions, and then there's special repeat forms where you do it over and over again. And we're going to cover those in a second. Amy, fail. Okay. Katie?
Matt stole my decrement as well.
All right. So 2x decrement, 2x mul. And actually, Dave also had negation, I believe.
Yeah.
Right? And yeah, I'll pull yours up in a second because he found a very interesting thing that, like, I have no idea why the compiler generated it, but, you know, I will ask the studio audience and or the internet's audience to explain it to me later. But, all right.
Leave.
That's right. You did find a leave, but we're going to cover leave in 2 examples from now. But leave equals which direction? E, SP, EBP. No. SP. So we'll see this in just a second, this leave instruction, but it's actually the equivalent of those 2 sort of teardown instructions that we see at the end of code, where you move to get rid of all your local variables, and then you pop the stack frame. All right. Andrew?
Well, I saw 2, but I guess the simpler one was branch if not equal using an if-else.
Okay, so wait, branch if not equal.
BNE?
So it was an actual BNE. Yeah? BNE. And yeah, so that's. We have branch if not equal in Intel? Yeah? I feel like there was like conditional moves and stuff like that, but I didn't remember there was that. 1 second. Let's see how that differs from a jump if not equal, for instance. I'm not seeing BNE.
Does it matter that I did it on my older Mac?
Yes.
That
Was
might
it a
be
Power
Motorola.
PC?
That might be Motorola then.
Yes, I think so.
So then I guess that.
Yeah, so you were probably disassembling like PowerPC or something like that. Was it like a G4, G5 or something?
Yeah.
G5?
Yeah, it's G5.
Yep. All right, well, Andrew found some
Epic
PowerPC
fail.
assembly, which we definitely don't
So
have.
I guess that PEA was also Motorola?
The what?
PEA?
Yeah. So that's why, that's why it's so suspicious all of a sudden you said BNE, and I was like, wait, you remember my example for Realms from 1996 where I said I was, you know, modifying some instruction sequence on an old Mac? Yeah, that sounded very not right. Okay, well. Ariel?
Yes.
What did you find last time?
Several. The most interesting of which was, oddly not on this sheet because I apparently printed out the wrong version. I want to say MOVSWL.
MOVSW. Yeah, so this is, well, I think this is move, well, yeah, okay, I'm not sure. I'm going to look that up quick. I would think this is move with sign extension, and the thing is, you probably did it on Linux, right?
Yes.
Yeah, so the thing is, with Linux, sometimes, like that W on there, that's not actually part of the mnemonic. That's something like Linux will add on like lengths in order to say like this instruction is moving a word, or this instruction is moving along.
I found a whole bunch that were move L's and
Exactly.
add L's and compare
So
L's.
all the
I said,
move
those
L's-
probably don't count.
Yeah, those are all just moves and adds and stuff, and in AT&T syntax you can tack on a little thing that says like, so I've been leaving it off of all of our examples thus far, and oh, I forgot to return that on. I've been leaving it off of our examples thus far, but in AT&T or Intel syntax, for instance, we'll often, it'll say like move double word pointer, but I've been like leaving the double word pointer off thus far. So let's do something like, all right, when this comes up, you can see it there. Yep. All right, so I've kind of been eliding this fact on our Intel syntax thus far, but if you look at our move instructions here, we have move, and it says D word pointer, and then the stuff inside the angle brackets, which we were talking about yesterday. And the D word pointer is what's telling us actually what the size is, right? And so in that case, for Linux, it's trying to say, move. Probably that's a move S, like sign extend, I think.
It may
No,
be
move.
short, because that was in fact what I changed that got it that.
Right, and the thing is on Linux, again, their word sizes, like GDB's word sizes don't correspond to Intel's word sizes. Like a 32-bit is a word in GDB, and 16 bits is a word for Intel. So, but let me see here quick, because actually that's probably, it was just move SW, right?
Okay, I printed out the wrong one, so I'll have to look it up again.
Yeah, I think that's actually a form, that's like a single form of something we're going to learn about in 2 examples again. It's like the non-repeated form of a move string.
Yeah, move string was what I've been hoping for, but I got very confused as to why I got it, because all I'm doing is dealing with printf and an integer increment.
Right. Yeah, so I believe it's this move S instruction, and then it's really just a question of what size it is. It's probably this one, and we'll go into that a little later. But this is sort of like what Amy was talking about. There's these string instructions, and there's single forms of them, but then there's also repeated forms, which is what we're going to be covering in a little bit. All right, anyways, anything else other than variants on stuff with things tacked onto the end of the mnemonic? No? Okay. All right, question?
I wondered when we were going through the conditional logic and jumps, is there an actual loop or an actual conditional assembly instruction?
What do you mean conditional? So there was one conditional jump within that loop. So there was the jump greater than or equal to, which was the comparison if I is greater than or equal to 10.
Yeah, but then you had to repeat the jump instruction in every case. Is there some kind of loop assembly instruction?
Yes. If you're asking if there's like a specific assembly instruction that'll just loop, there's kind of 2 forms. One, there is like literally one called loop, and I have never seen that actually used in practice. And then 2, there's this looping sort of string operation where you're doing the same thing over and over, but that's not the same thing where you can do complex logic in between things. So with these repeated string moves and stuff, if you just want to copy some data, you can loop and repeat that over and over, and that's what we'll see in 2 examples. But there is also an actual loop instruction. So I've never really went and looked at the details of that since I've never actually seen it, but I'll bring it up a little bit later.
So
yes?
A question about homework, which is that I tried for about an hour to get my compiler to output an ink or a deck.
Yep.
And I would reliably get it to either add or subtract 1.
Yep. And so actually, Greg on the phone had said he found a ink actually.
Maybe you should check
And I do.
All right, so Greg said he found an ink when he turned on optimizations, for instance, on Visual Studio. And I was actually surprised by that because according to the Intel optimization guidelines, it says, please do not use the ink instruction because of some flag setting that doesn't happen the same way whether you do an add 1 versus an ink. So I don't think I have like the optimization manuals added in with the rest of the manuals. So I can't just show that. But I'll put that down as another thing to bring up at the break. Show what the Intel manuals say about ink. I don't know if they say the same thing about DEC, but they probably do. All right. All right, so let's go to the phones. All right, so Greg, wait, was it Greg who found that? Who found the ink on the phone? I can't remember.
Yeah, that was me.
Okay.
Sorry.
And did you find any other instructions?
No, I didn't.
Okay. All right, so Greg found an ink when he turned on. Okay, well, hold on a second. This is. So we don't care about the W here. The move S instruction is move string, kind of like move string, but what it really does is it does move, and we'll say that it's going to be a D word size. So move a D word from ESI, the source. So actually, you know, whatever memory is pointed to by ESI, to EDI, destination. So it moves just a single D word. And then Greg found ink, which is I'm actually going to look that up quick to see whether or not that ink or deck can work on memory, or if it's just a register. Oh yeah, there we go. So ink has an RM32 form. So ink or deck can both work on a register or memory. All right. Brad, let's see. You found the mul instruction. Was that the only thing?
Well, I realized based on the conversation you just had about looping that the other thing I found was the rep STOS, and you're going to get to that in a little bit, but that was the other part of the program that I found.
So he found rep STOS. We're going to talk about that in the next instruction, next example. All right, Grant, what did you find? And Bill, can you turn up the speakers, by the way?
Sure.
Grant, what did you find?
I don't see him pushing his microphone, so I'm not quite sure if he's
right.
available.
John, what did you find?
I've actually found three.
Okay.
Repeat not equal, clear directional flag, and then jumps if not 0. I wasn't sure if the repeat and the jumps counted.
Okay, hold on a second. So you found rep not equal. What's that exact mnemonic?
Right. Rep
Okay.
any.
And then clear directional flag. Yep.
And then J and Z.
Okay. And yeah, J and Z, like we talked about yesterday, the Z is the same thing as the E. So jump not equal, jump not 0, same thing. So this is a variant on those conditional things that we saw yesterday. Clear directional flag. I put that? No. That was another one that that Dave found, and in his code I had no idea. What did you do to get the clear directional flag? What sort of C code?
So this was code looking to identify the VGA driver to see if you could identify the manufacturer of your video card, and it came at the end of a process.
Sure. Well then, you know, did that come, for instance, like before the rep not E, rep any? Or did it come after or anything like that? Was it like directly proximate to the rep instruction? Because that would at least make sense, unlike Dave's example. Do you recall if that was proximate or not?
Well, I just went back and looked at the code. There's a process that starts off, and it was the very last command in the process to close out the process.
Really? Interesting. That doesn't really make much sense either.
I mean, I can email you the source if you want.
Yeah, please do. All right. Justin, what did you find?
I was able to find the negate NEG instruction.
Was that the only one? Okay.
Yeah, that's all.
So we can see 3 negates, you know, 2 decrements, 1 increment. So maybe these are additional things you might want to at least be aware of, right? They're not particularly complicated, easy to learn, right? negate. Sorry, we're not done yet. I know, Nathan, I'll come back to you, but just as a comment, because, you know, we're already to 3x of something now. So like I said, three negates. Negate, very simple. It just says take a positive number, make it negative. You know, two decrements. Decrement and increment are just, you know, take a register or a memory value and add one or subtract one from it. And then we've got some rep type instructions down there. See more later. All right, Nathan?
I also found the rep and STOS instruction.
So just so rep STOS is actually considered like one instruction. So just that one instruction? Just that one instruction?
Yeah, I was under the impression it was two, so I guess I learned something.
Yeah, so it is kind of one instruction, or you can think of it like a modified form of just the STOS instruction with a prefix. The rep is actually kind of a prefix, so that's fine. It's a prefix which only works with specific instructions that end with that S, that move S, rep S, the NE, I guess, but that's the exception. And then, let's see, below Nathan, I think maybe Jeff is going to be there. Jeff, what did you find? No, we don't have Jeff online today. So, Victor, what did you find?
I guess you can add me to the list of negate functions. That's the only one.
All right, so you found an egg as well. All right. So, 4x. Everyone go out and learn how to turn positive numbers into negative numbers. All right. So, let's see. Just to go down these again, like I said, positive and negative. Unsigned multiply. It seems you can get this when you go ahead and use 64-bit values. Then it'll start generating that, and I'll actually show some code. It doesn't generate it directly, at least on Visual Studio. It seems to make you call a little multiply function which uses it. Decrement's a single register or memory location. Leave, we'll see in a little bit here. It's basically just the equivalent of these two instructions, move EBP to ESP, which gets rid of all your local variables, and then pop EBP. Move S, this is move a string, which in this case, without a rep in front of it, does EDI to ESI. Increment, just add one to memory or register. Rep stos, we'll see it in a second. This is repeat store to string. Or store, yeah, I think store to string. Rep NE, that's fairly uncommon actually. Well, I don't know if it's uncommon, just I don't see this very frequently. So I have to probably look that up to make sure I'm describing it right. Clear directional flag. So amongst those many flags, which I said you don't need to know about, there is one called the directional flag, and this one's kind of interesting. And because two people found it, I'll get into this today in the context of this rep stos and rep move, which we'll learn about in a second. And then jump not zero, aka jump not equal, things like that. So I want to quickly bring up the mul example code that Brad sent me. All right, so in my scratch pad, I copied over what he sent me. All right, so you can see here I have unsigned longs. These are 64-bit values. And so he's just setting something equal to A, setting something equal to B, and having a equivalently sized thing that he's going to store them both into. So A times B equals C. So we're going to set a breakpoint on that. And we're going to set scratchpad to be the thing we're debugging. Start it up. All right, go to the disassembly. All right, and the first thing we see is standard function prolog. Then we see subtract hex 18 from ESP. That's 3 times these 64-bit values, or 3 times 8 things. I think that's right. Yep. So 3 times 8 is 1/8, 16 plus 8. All right, so that's allocating space for the A, B, and C. And then what it does is it takes hex 32, which is 50, and puts it into EBP. Wait. Yeah, okay. So hex 32, which is 50, puts it into EBP minus 8. which is the lower 32 bits of A, and then it puts 0 into the upper 32 bits. Right? Again, hex 46, which is 70, into the lower 32 bits, 0 into the upper 32 bits. And then finally, what it does is it's basically going to get those values into EAX, ECX, EDX, and then it's going to be pushing each of these onto the stack. So that basically it's generating this call instruction. It's not going to like just do the mul instruction straight up, and I don't know why, but and actually interestingly, this one's not telling me the name of this thing. When I was doing it on my own machine, it told me that it was like underscore allmul or something like that, like underscore ALLMUL. So anyways, I guess this is a little, maybe it's because I don't know why that is. But anyways, turns out that Visual Studio doesn't just do the straight up mul, it pushes these two values that it wants to multiply to some generic multiply function. So we pushed, you know, all of the stuff. And when I come down here and I step into this, it's going to say, where's this, you know, assembly for this? Maybe it was LLmul and not allmul. I may be misremembering. So it's saying, you know, where's your source code? You're going to jump into some function that's not your function. Where's the source code? I say, I don't know. All right, so I step in here, and the main thing we want to see just is that, you know, eventually it gets to a mul. So either right here or right there. You know, so there's this jump not equal here. It's going to do some comparison. Jump not equal. It's either going to skip this first mul and go down to the second one, or it's going to do the first one. So got this little function in here which has a variety of different muls it can hit under different conditions, which I haven't analyzed, but the point is we eventually do get this unsigned mul when we're working with these long longs. All right, and then I wanted to bring up Dave's example code. Where did I put that? All right, so he did this sort of function. He had, you know, he used the absolute value function, and he put the absolute values A and B into these things, and then he had C, and then he took C equals A mod B, right? So remember the percent sign is mod in C, which says, you know, I want only to keep the remainder, right? So I'm basically doing a division, and then I only want the remainder of the result, basically. So he did A mod B and then just returned that C. And I guess he called Bob using values from his main, the 0, and, well, using 4 and 9. Passed those in and then did absolute value of 4 and 9 and put that in there, and then did 4 mod 9. I believe that's correct, right? So 4, 9, 4, 9. Yep. Did 4 mod 9. All right, and then he did GCC just to compile this. And then he used objdump in order to dump it out, but he obviously did this on, you know, some 64-bit systems, so we get nice 64-bit values and things like that. But, you know, he was nice enough to put little arrows here where he said, here's our new things, right? And so this is just a 64-bit negate. It's got that L on it because, like I said, when we get to the AT&T syntax, they like to put, you know, things, just specifiers for length directly onto the mnemonic. So we found a negate instruction. Wait, you said this was clear the directional flag, but is that true? TLTD? I need to check that quick. Make sure there's nothing that has a T in it. Let's see, this is literally 99. It's not that. Simultaneously, this one is FC. I don't know if that's the clear the direction flag, unless it's like... That's not 99, and that's not 99. So this is interesting. In this case, like, so I have some ambiguity here where I'm trying to say, well, normally when I would expect to see the clear direction flag, it would just be CLD, right? But this is CLTD, and so I say, okay, is this just the Intel syntax or the AT&T syntax using a different, like, mnemonic is, you know, so each disassembler gets to choose what mnemonic it wants to use to describe instructions, right? And so then there's the sequence of bytes, which I said, you know, thus far I've just been hiding from you, and I've talked about immediates are like hard-coded into instructions, but, you know, we haven't really seen it. This is an example. This is an immediate of a 0 hard-coded into an instruction. But so I can use these bytes to then go back, you know, so if I'm a disassembler, I use this byte sequence to say what instruction is what, basically. So the thing here is I see 99, and that's not corresponding to this byte sequence, and that's not corresponding to that byte sequence. So I'm going to, at the break, I'm going to go and dig into this one. And there's a little table at the very end, which you can use to reverse look up from bytes to instructions and stuff like that, but I don't want to get into that at the moment. So where's my note sheet? Yep.
Hey, Zeno, this is Brad. I saw something online that said convert signed long to signed double long.
Converts, so when you looked up the CLTD or whatever? Convert signed long to convert to double long is what you said?
Yeah, I don't know if that makes sense in this case or not, but it was an explanation.
Well, it probably does make more sense than just clearing the direction flag here, but... all right, well, I'm going to check that still at the break. So, but, you know, since someone else did find the clear direction flag, I'll just say here that that's what the CLD does. There's this D flag in the E flags register, and you can either set or clear it specifically with these instructions. So the previous flags we were talking about, they were all things which get set automatically through instructions. This is something where you can flip a flag one way or the other, because this direction flag actually controls the way that certain operations occur. It'll say if direction flag is set, if it's set to 0, then these next instructions we're going to see go from low to high, and if it's set to 1, instructions go high to low. So we'll get into that again when we cover these next examples. All right. So going back. All right, so this is where we left off yesterday. We were going to get into example 8. Make sure this is fine. All right. So here's a very simple example in which turns out to be fairly complex if we don't turn off those various sanity checks and things like that in the debug build of Visual Studio. So we are just going to allocate enough space for a buffer which is 40 bytes long. Then we're going to take the number 42 and we're going to move it into the last entry of the buffer. And then there will be hex blood. So if we compile this, we get this. And so we want to dig into this and figure out what the deal is with this. But first we have a new instruction, the rep stas, or repeat store to string. So we need to talk about that. All right, so as was said before, there are certain family of string instructions for which you can use rep as a prefix, basically, and it's saying repeat this instruction over and over. So there is just a plain store to string, and I can't remember, did someone find that? No. So Ariel found move s, which is a version of this that we'll see in the next example, but so there is a standalone STOS instruction, store to string, but we usually see these sort of instructions in their repeat form, where they have rep before them and then store to string. So for the rep instructions, what they are is they're functionally they're looping and doing the store to string operation multiple times over and over again. Under certain conditions. So the primary condition is that now we finally are going to see ECX being used per that register convention that we talked about at the beginning. So we said ECX can act like a counter for something, and this is where it acts as a counter. So with the repstos instruction, you would initialize ECX to the number of times that you want to perform the stos action, and then when you execute the repstos, it just keeps going and it decrements ECX one time for each time it does the stos action. So specifically, what the stos action does is it will either fill, 1 byte pointed to by EDI with whatever value is in AX. Right? So remember, yeah, that doesn't make any sense. It can't be a byte if it's AX. AX is 16 bits. Like I said, I love finding bugs every time I go through this. All right, element of P. Yeah. So it can either be, technically, I guess you can move 1 byte at a time or 1 D word at a time. Technically, there's a 16-bit form, but we're going to pretend there's not. So we're going to say it's either moving 1 byte or 1 D word at a time. But you have to do something special to get the 16-bit version anyways. So we're going to ignore that for the moment. All right, so let's try AL. If you're going to be using your printed slides, fix that. All right, so you can take 1 byte from AL, which is that lowest byte of the EAX register, right? And we're going to put that into memory wherever EDI is pointing right now. So that's the core version of stos, is either take 1 byte from AL, stick it into memory at EDI, or take 4 bytes from EAX and stick it into memory at wherever EDI points to. And when it does that, automatic So automatic within this rep construct is the fact that after it moves this 1 byte or 4 bytes from EAX into EDI, we'll just talk about the 4 byte version from now on. It moves 4 bytes into memory pointed to by EDI. It decrements ECX by 1, and then it increments EDI by 4. So it's sort of like you have some pointer to EDI, you copy 4 bytes there, and then you move EDI up, and you decrement ECX. So it's saying the ECX is the counter, so it's like I did it 1 time, so I must decrement ECX by 1. And then EDI is your destination, and EDI just keeps moving up. EDI, hold on a sec. So EDI is basically like this pointer which keeps getting incremented each time through the loop. ECX is your loop counter. It keeps getting decremented each time through the loop. And basically this instruction stops doing the same thing over and over once ECX gets to 0. So when ECX, the counter, finally hits 0, you move past this repstos instruction to the next instruction. But as long as ECX is greater than 0, it just keeps moving, 4 bytes from EAX to EDI, and then increments EDI, then moves 4 bytes, then increments it, then moves 4 bytes, then increments it. So basically, over and over, this is a thing. So what you can think of this here, like in C notion, is like a 1 instruction memset, right? That's the word I'm thinking of. Memset, right? So you have the memset instruction, which says, I want, when you call the C function memset, you give it a pointer to where to start. You give it a value that you want to set all this memory to, 0, CC, whatever. And then you say, here's the size that I want to set, right? So this is basically a one instruction version of that. You give it an EDI where you want to start. You give it a count. ECX is the count of the number of times you're going to set something. And then whatever you put into EAX, that's what it's going to just keep writing to memory over and over and incrementing as you go along. So basically, I call it a one instruction version of memset, but really there's a little bit of setup that has to go on before it, right? So 1, you got to set ECX to however many times you want to copy this value. 2, you got to set EAX to whatever you want to write to memory. And what did I say? There's 3. Set EDI, set EAX. Right, so set the destination, set the EAX value, and set ECX to the number of times to copy, right? So I think I actually said 3 and I didn't count to 3. Yep. So set your destination, set your value to copy, and then set the size to copy, which is really just ECX, which is the number of times you want to do it. And so the size is really just however many times you want to do it divided by whatever size you're writing. So you could be writing 1 byte at a time, in which case you'd set ECX to the total size, right? Or if you're doing it 4 bytes at a time, then you kind of have the size needs to be divided by 4 because it's going to write 4 bytes. So it's not going to decrement ECX by 4 when you write 4 bytes. It's going to decrement ECX by 1. So it says, I wrote 4 bytes, decrement ECX by 1. So ECX is always decremented by 1. But EDI is incremented by either 1 or 4, depending on what form you're using at the moment. So, I said, we'll pretend there's only 2 forms. There's actually a 16-bit form as well. But you can just think of it like there's one form where the instruction you're actually doing says, I'm only copying 1 byte at a time, and the other form says 4 bytes at a time. So anyways, let's see that in the context of this previous thing. I guess I have all the description here. Well, so I guess here I just say that within that assembly that we saw, here's where it's doing each of the things that you need to do to set up a rep stos, right? So we set the destination EDI, so we have some value, whatever it is, we move it into EDI, right, using an LEA. We move hex 3C into EAX and set the count, and then we move some value into EAX, sorry, that was ECX. Move some value into EAX in order to set the value that I want to write to memory. In this case, they chose to set all the memory to hex C, and then finally we execute the rep stos. So we're going to go look at that in the context of what's actually happening here and try to understand, like, okay, this was our assembly code, or our C code, and why do we get what we get here? And I'm going to draw sort of a stack frame picture for this.
Hey, Zeno, is there any reason why they chose C?
Yes, so there is a reason why they chose C, and I'll talk about that. Well, I'll talk about it now. They chose C because in the single byte CC, that corresponds to the interrupt 3 instruction. So if you go to interrupts, CC is interrupt 3. Interrupt 3 is the breakpoint interrupt, actually. So when we click and set breakpoints, it's really the debugger is sticking in a little CC right there so that when the instruction gets hit, it fires off an interrupt. The debugger catches the interrupt and says, aha, I hit a debug breakpoint. I need to stop stuff. I need to update, whatever. So we talk about interrupts a lot more in the intermediate x86 class as well as the breakpoint interrupt. But basically the reason why they're using the CC is they're going to be initializing memory to this. It's going to be setting a big initialization, and it's kind of like for 2 purposes. One, if you ever read from this memory, they can say, okay, you just read from something which is CC, you should have never read from that, that's just my initialization value. And 2, if you really screw up your program and you do some buffer overflow or something and you accidentally jump into this code here, so if you accidentally somehow set the instruction pointer to this memory which is being initialized, then you're going to hit a breakpoint and it'll immediately break into the debugger, and you'll be like, why am I here right now? Why did I get a debug breakpoint? I don't have a debug breakpoint here, but it's because you messed up your code and you jumped into somewhere you shouldn't have. And so this is kind of like a catch-all way of sticking a bunch of breakpoints in there so that if you accidentally screw up and go somewhere you're not supposed to, you'll get a breakpoint, and also it's to initialize values so that it can check whether or not you've screwed up your stack. So see that function at the end, the RTC check stack vars. Later on it's going to go back and say, we're not going to step into that function, but it's going to go back and it's going to say, I set some CCs right here, and if they're not currently CCs, that means you probably buffer overflowed your stack, because as we'll see when we get into this this picture of the stack as it's doing this instruction, you'll see it's kind of setting guards on either side of that buffer that we allocated, so that if you ever write outside of your buffer, it checks that at the end. So to be clear, this is not like a security check. This is literally just a sanity check. That buffer security check that we did before is the security check. This, since it has a fixed value, there's nothing particularly preventing an attacker from, you know, writing CCs. The attacker would know what he would have to write in order to make sure that he doesn't fail the sanity check, whereas the security version has a random value rather than a fixed value. But we'll talk about that later. All right, so I'm going to start out at the top of main. Let's see, where do I have most stuff down? All right, start at the top of main. We have the saved return for whoever called main. All right, so saved EIP from the initialization code which called main. First thing we do is push EBP. So now we have saved EBP, that's our first instruction, right? Set the stack pointer equal to the frame pointer. So initially, right now we have this equals EBP after we do the move ESP to EBP, right? ESP is right here right now, and EBP. So this is right now after the, maybe I should somehow highlight where I am. I'll do it this way. All right, so after that instruction, that's the thing that we see on the stack. So now I'm going to do the sub instruction. So sub hex 30 from ESP. And I believe hex 30 is 48 bytes. And remember, we have a 40 byte buffer. We have char, whatever it was, buffer 40 bytes, right? So this thing's over allocating extra space, essentially. So this is hex 30 equals 48 bytes. So we did ESP minus hex 30. So now ESP is down here. So this is ESP, aka EBP minus hex 30. All right, so that just allocated some space for this local variable, but we can see it allocated too much space. All right, then we have push EDI. Okay, so that does, that is confirming that I had my variables in the wrong version. All right, so this is saved EDI. All right, anyone tell me why we're pushing EDI in this case? Yep.
We're going to pop that again later.
Yep, so she said we're going to overwrite it, and we'd like to make sure it doesn't get overwritten. And key point she said is we're going to pop that value later, right? So down at the bottom, this is our confirmation that EDI is a callee saved register. So it's like main right now is the callee of something else, right? Someone called main. And so main right away at the beginning is saying, look, I'm the callee, but I know I want to use EDI. And so I better not screw up EDI for the guy who called me. So I'm going to save it right away, and I'm going to pop it at the end. And that's the popping at the end is why the save and restore is why you know that it's some sort of caller, callee, save kind of thing going on here. All right, so pushed EDI. We've got that on our stack below our local variables. And now we're going to do, well, and the other question is, can anyone tell me why I want to use EDI right now? You know, why must I save EDI? Why do I know automatically that I'm going to destroy EDI? Yes?
That's what's being used by STOS, isn't it?
Right, yep. So we know that we're going to use a rep, well, the compiler knows it wants to use a rep STOS instruction. And the rep STOS instruction always uses EDI as the destination for its copying, right? So it has to use EDI. It has no other choices in what registers it can use. And therefore, it needs to save it off so that it doesn't destroy it for the caller. All right, so anyways, then we're going to do an LEA of EBP minus 30 into EDI, right? So right now, stack pointer is actually down here. Stack pointer moved down. So this is still pointing to well, there's nothing pointing to this right now. This is just for my own benefit. I noted that when we subtracted hex 30 from ESP, which was EBP at the time, this location right here happens to be EBP minus 30. And then, ESP, then when we did the push, EDI, ESP got down here. All right, so got our ESP down here, and now we have an LEA, EBP minus 30 into EDI, right? And so remember, LEA, we're not going to memory at that location. We just want to know what's this address right here. And that is sort of, the address of the bottom of whatever this space was, right? So we're just going to take this address right here. We'll make up some value for it. We'll say it's going to be, 12FF, 20 or something. I don't know, right? And so we're going to move that into EDI. And so we're going to say, right now, essentially, EDI points here as well. I guess I didn't really need to write a fake value because we don't really care what it is. All we care is EDI right now points at the bottom of this allocation space, right? And then we, again, we can see bam, 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 set EDI, set ECX, set EAX, right? Right in front of that rep stas. So we set EDI to EBP minus 30 right there. We're going to set ECX to hex C, right? So ECX equals hex C. And then we're going to set EAX to CCCC. EAX equals CCCC. Right. All right, so, and then now this is, like I said, thus far I've been kind of not making a big deal of this, but when you want to know what form a given instruction is in Intel syntax, there is this portion in here which will frequently say, D word pointer, right? So it's going to say this is going to be operating on D words 4 bytes at a time. So I said there's a version of repstos where it's doing 1 byte at a time. That one would say byte pointer. This one says D word pointer. Therefore, it's doing 4 bytes at a time. So given the fact that it's doing 4 bytes at a time, right? What can we say about, where's my copy going to stop here? Right, so I'm going to copy 4 bytes at a time, XC times, so how many bytes am I copying? 48, yes. 12 times 4, 48. So this is 48, right? My size is essentially 48 divided by 4, right? Because I said the ECX is just a counter of how many times you're going to do it. It doesn't care about whether you're incrementing by 4 or incrementing by 1. But the compiler needs to care about that, right? So the compiler needs to know if I'm going to copy 48 bytes, 4 bytes at a time, I better, not put in 48. Otherwise, I'm just going to keep going way too far, right? So the compiler definitely knows to make sure that the sizes all line up. If I'm going to use a 4-byte copy, divide my size by 4, right? So anyways, what's this going to do? It's going to put, C, all the way home. Right? All that's going to be CCC. When you get to the end, EDI is going to be pointing here. Well, I guess EDI will be pointing at the next thing past that because, well, I guess I don't know whether it does a post increment or pre-increment on the last time. So EDI is in quantum superposition, and it is simultaneously both there and there until I find out where it would actually be. And I guess I can do that pretty easily by just stepping through this code. All right. So anyways, then after the repstos, we just saw all of that set. All right. Now we're going to see hex 2A, which happens to be 42, moved that into EBP minus 5. All right. So this is EBP. We know EBP minus 4 is 4 bytes down right there. And then we have EBP minus 5. EBP minus 5. So, I can draw this different ways, but I'm going to say that, in the way I'm drawing this, I'll divide this up by 4, right? And I'll say this is memory. So I'm going to say little end is put first. So I'm going to be saying, you know, -5 is right here, and then -4 is right here. So I'm going to call that -4. I'm going to say, you know, this position is the actual -4, and this position is the -3. This position is the -2, and that's the -1. This is the -5, and that's the -6, and that's the -7. That's the -8, right? So EBP -5, we'll say, is right here, right? And what's it doing? It's putting hex 2A into that, right? So I'm going to put hex 2A into that. And what does that tell us about, you know, the actual buffer that was in our original C code, right? So back to our original C code. We had buff of 40, and we have the 39th entry, the last entry of the buffer, set to 42, right? So what that can tell us is EBP -5, this thing right here, is the 39, you know, the index 39 of buffer, right? So if I counted back the way that I'm counting, I could go all the way down here, I believe, right? So this would be, well, so, I mean, I'm counting the opposite direction. Those were EBP minus things, right? But this is index 0 in buff. Well, all that. Buff of 0 is down there, and that right there is buff of 39, right? But actually, the thing is here, right, we have a 40-byte buffer, but we allocated 48 bytes, right? So there's actually 4 bytes on this side, and there's 4 bytes on this side, and then there's this 40-byte buffer in the middle here, right? So we didn't set any of the rest of this buffer, so the rest is all defaulting to CCC right now. We only set this last element of it, right? And then we just return, right? But you can kind of see this is the way that the compiler has chosen to generate this code. It over-allocated space with a space on the front and space on the, well, space above and space below. And it's got CCCs above and it's got CCCs below. Sorry, above and below, right? So again, just gonna wipe those out. This is all C, 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 C. And then, yes, question.
So, what purpose is that serving? Because it's not going to help against an intentional buffer overflow attack.
Right, exactly, and that's what I said. So this is not a buffer overflow thing. This is just a sanity check thing, so that when a programmer is sitting in their Visual Studio environment, when you get done with your code, so here's the thing, right? There's 2 instructions worth of real work here. There's setting buff 39 equal to 42, and then there's returning hex blood. And then everything after that is now, you can think of it like teardown, right? And you can see within that teardown is this call to this RTC, runtime C, function called check stack vars. Right, so we might have a notion, I mean, I don't think I've ever actually dove into it. We could if you want, but we can have the notion that this thing is going to be checking, you know, stuff on either side of this buffer. It probably only checks this one, actually, because typically your buffer overflows, right? They overflow that way. So it's not worried about malicious buffer overflows that are trying to, like, gain control of the program. They're just worried about the programmer screwing something up. So if the programmer screws something up and copies too much data to their buffer for whatever reason, if there was like a mem copy or something like that in their code, right, then they could potentially screw up this CCC here. And then that function at the end is going to say, I know that I have at EBP -4, I know I better have CCCC. If I don't, I'm going to prompt the developer, and I'm going to say, error, your stack variables are corrupted, fix your code, right? So that's the basics of it. So actually, I'm going to step through this quick because I want to see where EDI is at the end. I don't know why I wrote ESI. Exactitude matters in assembly language. Which is bad because I'm good at simple mistakes. All right. So this is example 8, I believe. Yep. Bam. Run it. All right. So we can see this is, this is the version that has the sanity check in it. We got all of our CCCs and all that. So I'm up here. I'm going to do bam, 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 bam. And then now I said I wanted to know where EDI is going to be at the end of this, whether it's going to point. Essentially, I want to know whether it points at EBP or EBP minus 4, right? So I can just step over this. Actually, let's see. If I step into, let's see if it does one at a time. Yep. So if I step into, sorry, let's go ESP right here. I set that to refresh, right? So if I step into this rep stos, you can see CC gets copied, CC gets copied, CC gets copied, right there. For each time I step into, the debugger will actually let me, stop after each instance of this copy. Or I could just step over, and then bam, everything gets set to CC for 48 bytes. All right, and then I guess I wanted to know, does EDI point at EBP or thing past it? And yes, it does point. So EDI, even for the last iteration, basically, I was trying to determine, for the last iteration, it still increments EDI, and then it checks ECX is equal to 0. So EDI points up here. It did, 48, or it did hex C hex C copies, but then after that, it was still, 4 bytes beyond where it actually was copying. And so now let's kind of step into the actual sanity check function here at the end. I don't know where my symbols went today. All right, so step over, smash. Try that again. All right, so I'm at the call instruction, and so I'm going to step into this because I don't really know what it does. And then let's take a gander here. Well, I can see right there's a compare against CCCC, right? So it's checking something to say, is it still CCCC? And there's another compare against CCCC. And then I would guess this call is probably like a call to like, you failed or something like that. Pop up a box that says like, you fail. Otherwise, if you don't call that, then you probably eventually hit this return instruction, right? So, like I said, basically it looks like it's, checking values to make sure that they're still equal to CCC. I guess I can smash this manually and we'll see what happens here. So, there's my 2A, right? That's my 42 that I copied into that 39th position, the 39th index into the thing. But, like I said, I suspected this CCC after the buffer is what they're looking for to make sure that, like, you didn't overflow it. So I'm going to set that to, like, something else, like zeros. All right. I'm going to step through the code, and I'm going to assume it's eventually going to pop something up and say you screwed up your stack. So just going to step over and see which branches it takes. All right, well, it did a first compare, EDI versus ESI, whatever. All right. And now here's just an interesting point here, right? You can have the jump less than or equal be displaced from the compare, right? And this is where, you may ask yourself, okay, well, did these move instructions set any flags that this thing cares about? I'm going to say probably not, even though this is displaced. If this jump was based on these move instructions, which were immediately before it, right, then there would be no point to be doing a compare anyways, right? So, my intuition here says it's really this compare back a couple of instructions ago, which is what the jump is actually jumping based on. And this is, again, one of those cases where I could go try to find the flags, and there is a flags thing right here, but I definitely don't recommend using this because Microsoft decided to go with their own names for flags. So it's OV instead of the overflow flag, OF, which is what it should be. It's OV. And up equals 0. Up is the direction flag. They're saying the direction flag is currently set to 0, therefore it's up. And if I change the direction flag to 1, it would say DN or something, down. So whatever, the flags are ridiculous here. I typically don't use this at all. If I really have to have flags here, you got your E flags register there. I go back to the manual and I say which bit position is the flag that I care about. And I compare that against this X202, whatever. So anyways, like I say, normally I don't care what the flags are. I just go ahead and jump over it and see what it says. Okay, well, whatever. Didn't take that jump. Fine. Now I just did a compare. Okay, well, here I maybe want to see, like, what this is, right? So ECX plus EBX minus 4, and it's comparing that against CC. It's not giving it to me with mouse over, but I'm going to try like this. Well, what I'd do here is maybe open up another memory window, like so. Paste that in. Press return. Okay, well, this thing that it's comparing against right now, memory is currently CCC for this ECX plus EBX minus 4. So, this compare is going to be, something with itself. Compare instruction is a subtract. Subtract something from itself. It's going to set the 0 flag because the result is going to be 0. And so it's saying jump if not equal, jump if not 0. And therefore, we don't expect this is going to actually take the jump. And indeed, it fell through to the next instruction. But now this one is where I think it'll probably fail. All right, so EDX plus EBX. Let's see what's that memory there. Okay, that's my zeros, right? That's what I put in manually. And if I go up, right, there's the 2A, and there's my zeros. So it checked the buffer on one side, and now it's checking the buffer on the other side. It's going to fail on this. So I expect it's going to, this will be equal, these will not be the same thing. So the 0 flag will not be set. And so this jump equal will not be taken, I believe. Right, so it fell through, but now I fell through to what? Well, I said that call is probably the call to prompt the developer that you failed. Right, so let's go ahead and step over it. Oh, it didn't give me a nice little, oh well. I was hoping it would give me a dialog box. Well, I'm just going to get out of here. And maybe it'll prompt me later. Maybe that call just like set something somewhere that'll prompt me later. All right, maybe on the return. Nope. Tough luck. Oh, but I smashed my stack. Whatever. I don't know. Later on, you can go make your own example where you have a mem copy and just like copy way too much data. And I'm sure you'll see like a little prompt telling you messed up. All right, anyways, that was repstos. So, and then, okay, returning to that direction flag thing that I said, a couple of people found, potentially. Here's the interesting thing about the direction flag. By default, typically the direction flag is 0. When direction flag is 0, that means copy upwards from low to high. If the direction flag is manually set to 1, for instance, that means now these repeat instructions, which would normally increment EDI by 4. So whereas we said that the normal operation of these rep instructions is you increment EDI by the size of whatever you're copying each time, if you change the direction flag, it'll actually decrement EDI by the size of what you're copying each time. So you can have sort of a reverse copy where it copies from low to high. So I could have like set EDI up here, and then I could have set the direction flag to 1, and then it would have copied that direction. And the funny thing about this is I don't know if this is exploitable in any cases, maybe, maybe not. But typically the compiler to if the compiler is being good about things, it would, for instance, clear the direction flag immediately before the rep stos instruction. Because it would say, like, look, I know that this instruction sequence I've generated is going to target here, and I want it to go positive, right? If, you know, the guy before main was called, if that set the direction flag equal to 1, then that would totally screw up this copy, and it would copy in the wrong direction, basically. So potentially that could screw with stuff. Maybe, maybe not. Probably not in most cases, but you can probably induce some weird bugs by flipping the direction flag around, right? So maybe it's a small copy, right? Maybe instead of being like something where you're trying to smash a huge thing, maybe you've got buffer here, and maybe it's just a struct or something like that, and you've got struct here, and then, you know, so struct is here, and the thing thinks it's going to be copying from some other struct, like off in some pointer somewhere, to that struct right now. But instead, you flip to the direction flag somewhere, and now it copied onto that struct, except now it's in backwards order, so that could potentially mess with you. But you could be like smashing other local variables here, right? We had only one local variable in this case, but you know, your local variables are generally contiguous, right? And so if you have something which is doing a repeated copy over here, if you change the directions, you're potentially messing with other local data variables. And there is work out there that suggests that as opposed to your traditional buffer overflow where you're trying to go after that saved EIP in order to like control the instruction pointer, there was like a paper, I don't remember when, 2005 maybe, called Non-Control Flow Data Attacks Are Realistic. It was like out of Microsoft Research. And they basically said, like, look, in some cases where you're buffer overflowing and you're just overflowing into adjacent data, you're not like smashing the stack and destroying the EIP that's saved. In some cases, if you're just buffer overflowing into adjacent data, local variables, you're changing a local variable, and then that changes the control of the thing because, you know, there's some check that says if A equals whatever, right? And you've changed A to now not equal something, and therefore you're diverging the control flow path. So smashing local variables and stuff like that is a potential exploit path, but it's not the generic exploit path that smashing EIP is. So it's more of like an application-specific kind of attack that you would have to do. So anyways, that's the direction flag and its pertinence to rep stos. Any questions? Anyone on the phone have any questions? All right. So we're going to go on to the next example. All right, and oh, just as a pointing out, where this came from is like I left the basic runtime checks in Visual Studio, right? This is the thing where I told you to set it to default so that we turn off these two types of checks. One of them is stack frames, where it's checking to make sure you haven't, you know, messed with your stack frame. And the other one is the uninitialized variable. So if you create A and then you read from A before you've set anything into A, then it'll prompt you and say you've tried to access an uninitialized variable. And so again, if you turn off those sanity check basic runtime checks option, then you'll just get this code, which is very simple. Standard stack frame setup, allocation of space for your local, setting the last element of the local, which is now EBP -1, right? Because it bumps up directly against that saved EIP because you don't have that forced padding in between it. And then set EAX equal to blood and tear it down.